close the door, actually. So welcome. These lectures on quantum field theory will be a short set of lectures, 5 hours. Well, actually, quantum field theory is a difficult subject. It requires a good set of 2-semester course of lectures to really understand or to teach you everything about quantum field theory, and even then it may take a couple of years after that you really know what's going on. So it's rather an impossible task to condense quantum field theory in 5 hours, which is the number of lectures that I prepared. Actually, that may have been the reason why people at the announcement gave me twice of 2 hours per day. Namely, the announcement was at 10 o'clock until 12, but actually I'll give the lectures from 11 till 12 because, well, I did the work to condense field theory in 5 hours, and I won't re-expand it to 10 hours, so anyhow. Actually, just before the weekend, I lost my voice, so if you hear a little squeaky sound, that's not the microphone, it's my voice that's trying to break down. But anyhow, I'll give the lectures on the blackboard, so I'll try to go slowly and be as self-contained as possible, and I appreciate any questions that you have about, well, what I'm trying to explain. So quantum field theory is a theoretical framework for describing elementary particles and their interactions, and it's a combination of quantum mechanics, and special relativity. Combining these two ingredients gives you quantum field theory. And the aim of quantum field theory is, of course, to compute those quantities that we are interested in well, comparing to experiments. So what are those quantities? Well, since quantum field theory involves quantum mechanics, quantum field theory can compute for you probabilities. It can compute for you quantum mechanical probabilities. Well, that's not what we see in experiment. In experiments, we see events. So we see certain collisions that can happen, and we consider certain processes that involve particles coming in, say electron and a positron, and a number of particles coming out. And what quantum field theory should tell you, well, it's a device actually that fills in whatever happens in between and tells you the probability of a certain state of the electron and the positron to give a number of external particles that come out. And so the thing to compare now to experiment are not directly the quantum mechanical probabilities. What you see in an experiment gives you a number of events. And events are the things that you can count, and quantum mechanical probabilities are the things that you can compute. And then the thing that connects the two will be the cross-section. So an experimentalist doing an experiment can count events and eventually compute a cross-section from the way that the events are counted, and quantum field theory will be a way to, through the rules of quantum field theory, compute the cross-section. And what I will describe in these lectures is basically this set of connections between well, Well, first of all, starting with quantum mechanics and special relativity, this will be part of my first lecture. I will then, in the second lecture, tell you how to go really to quantum fields. In the third lecture, I will describe indeed how quantum mechanical probabilities and probability amplitudes actually can be connected, first of all, to cross-sections and how they are computed from the rules of quantum field theory. I will then go back to quantum field theory and describe in more detail what quantum field theory, how interactions are introduced in the form of Lagrangian field theory. And finally, I'll describe in the lectures the Feynman rules of quantum electrodynamics and compute some diagrams, loop diagrams, and discuss renormalization. But just to start, let me tell you a little bit about indeed what the object is that quantum field theory is computing, namely the cross-section. Just to give you already an idea what kind of issues are important. Actually, in discussing the cross-section, you'll indeed find some ingredients that are intuitively already at the right level to understand also where quantum field theory comes in. So we're looking at a certain, say, an experiment where two particles collide, electrons and positrons, and you want to know, at least evaluate the number of events that you get given a certain cross-section. And so the picture that you have then is that, say, if we have an electron and a positron, and I'll picture the positron having a certain size, which is a cross-section, have the cross-section, say, sigma, then what you can imagine that if the two particles move towards each other with a certain velocity v1 and velocity v2, then you can calculate the number of events that happen if the particles, the E plus particles and E minus particles, have a certain density, particle density, which I call ρ1, which is a function usually of x, but let me just for the moment assume it to be constant. So I have a density of particles ρ1 for the electron and a density ρ2 of particles for the positron. Then the number of events that you get, well, to calculate this, what you do is actually, well, I'm going to count number of events in a certain amount of time, delta t, and a certain amount of volume, delta v. So there's a certain amount of volume in space and a certain amount of time, and then you can calculate how many events you would see there. Well, the way it's related to the cross-section can be obtained like this. So we're going to look a little moment delta t later, and then the two particles have moved relative to each other, and then this positron has swept out a certain region of space, which, if you think about the perspective of the electron, is a region of space proportional to the velocity and the time. So it's a region of space which is proportional to the relative velocity v1 minus v2 times the time, because that's the amount of, that's the relative distance, how it has changed over time. And if I multiply this now with the cross-section, I'll get a volume, which is the volume swept out by the positron particle. Now, to calculate how many collisions have taken place, well, you have to multiply this, first of all, with the number of positrons in that volume, and that's to obtain that, you must multiply with the density of the number of positrons. And furthermore, I have to multiply this factor with the number of electrons in the volume delta V. So I'll get an additional factor, which is ρ1 times delta V. And that's the number of events that you have given the cross-section sigma. Well, this is only in the situation where indeed I have the simple picture of a constant velocity and a constant density. Well, usually actually the density, the particle density is a function of space and time. And also the velocity is not always constant everywhere in space, and it's actually more appropriate to think about a density current, or a particle density current, which tell you how the particles flow through space. So the density current tells you basically the velocity at a local point in space and time, and it's equal, you can think of it as being the density times the local velocity v. Well, the fact that particle number is conserved tells you that these quantities, the particle density and the particle current, density current, must satisfy a continuity law, conservation law, which is written like this. There's particle number conservation. This implies that the divergence of the current plus the time derivative of the density must be 0. And then you can apply a similar argument as I did here and compute the number of events by integrating over volume and time and express it in terms of the particle density and the currents. And the expression that you get is similar to this one. It's equal to the number of events that you get, n, is equal to the cross-section sigma times the integral over time of an object which is called the luminosity, where the luminosity L of t is the integral over space of a product of, first of all, the density of the first particle times the current density of the second particle minus the other way around. Absolute value. Actually, if you assume that J and rho are constant, and indeed J is equal to rho times V, then this expression is exactly equal to this expression over here, but just summing up all the contributions over time and volume. But just what I wanted to make clear in this is that indeed what you have to know in order to compute the number of events is something like a particle number, particle density, and a density current. Something that we have to know also in experiments. So the luminosity is something that you can measure. Once you know, for example, the cross-section for a particular event, then given the number of events, then if you know the cross-section, from that you can determine indeed the luminosity. But then after that you can also look at other events and determine the cross-section in the other way around. And this is the way that for an experiment you get information about this number, the cross-section. And it's this number that also quantum field theory should be able to compute, and then you can compare experiment and theory. So this was just about this part of the relation about the number of events and the cross-section. So now I'll start and describe how quantum mechanics and special relativity eventually should be put together so that we get a framework, quantum field theory, that can describe and compute these cross-sections from the point of view of the theory. So what do we know about quantum mechanics and special relativity? Well, quantum mechanics, I'll assume that we know indeed that there's something like a Schrödinger equation, and in special relativity I will use the basic definitions of energy and momentum that play a role in special relativity. Actually, the fact that two particles by colliding can indeed create many particles is something that can only happen when we have these relativistic quantum field theory, because what happens here is that the energy contained in the initial kinetic energy of the electron-positron pair is, of course, transformed into other particles using the fact that energy can be transformed into matter using Einstein's equation E is mc squared. So those, the fact that particles can be created is something that can only happen in special relativity. So relativity and quantum mechanics, to put them together, I will start from, first of all, not describing the motion of particles in terms of velocities. It's actually much more convenient if you think about, first of all, the particles that we encounter in high energy experiments, they have velocities in the speed in the neighborhood of the speed of light. And also momentum is the object that's conserved in collisions. So according to relativity, momentum P is equal to m times v, where v is the velocity, divided by 1 minus v squared over c squared. And the energy is related to the momentum by taking the square root of p squared c squared plus m squared c to the fourth. So where indeed when you put the momentum p to 0, you get the equation E is mc squared. So this is the momentum for a particle with mass m and velocity v, and this is the energy for a particle with mass m. Now, to describe the relativistic Schrödinger equation, what we're going to do is do the same thing that we do in usual quantum mechanics, namely, in quantum mechanics, what we usually do is we take the momentum p and replace it by an operator acting on a wave function. Wave functions are functions of x, so operators can be expressed in terms of derivatives of x. And so the usual way that we have p, the momentum is represented as an operator, which is the derivative with respect to the coordinates. So I'll denote derivatives in terms of, with respect to x coordinates in terms of nabla symbol. So this is the gradient differentiation with respect to x. So then we get a relativistic Schrödinger equation I'll abbreviate time derivatives as just as dt, acting on a wave function psi, which is a function of x and t. And then the Schrödinger equation tells you that this must be equal to the Hamiltonian acting on the wave function. And the Hamiltonian is just the energy, but then interpreted as an operator, where we take p and replace it by the derivative here. So in this case, you find that the Hamiltonian is equal to the square root of minus h bar squared then here I inserted indeed p. I replaced by h bar times the derivative. So in here, actually, you get the derivative squared, then m squared c to the fourth c squared. I put out a factor of c. Well, actually, in the following, I will start working with h bar equals c equals 1. So in order to simplify eventually the expressions, we're not going to write every time where the Planck's constant and the speed of light is in our expressions. So unlike the non-relativistic Schrödinger equation, we have here a Hamiltonian with a nasty expression because it's a square root of some differential operator. This makes it maybe hard to imagine that you can solve the equation easily, but indeed you can do it by just plugging in a plane wave solution. So we have as solutions plane waves. So that's a function psi k of x and t, which is just an exponential of I to the kx. And then there's a frequency I omega, which will be a function of k times t, where if you take this expression and insert it into the Schrödinger equation, what you can do is replace wherever we have the derivative, we put k, and wherever we have the time derivative, we get the frequency omega. So there will be a relation between, if we plug it in this expression, between omega and k, and the relation is that omega of k is c times the square root. Well, I'll drop indeed, put these conventions into effect. H bar c equals to 1. Then it will be the square root of k squared plus m squared. Continue here. So what I described there is just the simplest solution, but the most general solution you can obtain by taking linear combinations of those plane waves. So the general solution looks like psi of x and t will be an integral over k vectors, and then I'll put in a normalization which is twice omega k and e to the I kx minus omega t, and then there's a function that's a function of k. So any expression of this sort where I now have a wave function, which is a wave function expressed in a k momentum vector, will be a solution to the relativistic Schrödinger equation which I wrote over there. Actually, the solution, the omega of k, as I indicated, is the expression over there, the square root expression, and I want to stress the fact that it will only allow omega of k, again, to be the square root k squared plus m squared, but it's positive. It's a positive frequency because the wave functions that we allow here should be positive energy wave functions. Well, in here, I've now written down a wave function of a particle, a relativistic particle. So how is it related to objects that I've introduced here? Actually, if you have quantum mechanics, then having this wave function, it tells you something about the particle distribution in space, or in momentum space, if you wish, or in real space. And there's an expression indeed for the particle density, or the probability density that you get a particle once you know the quantum wave function. Now, the probability density should be a density just like the particle density, and there's a density current J which satisfy these conservation laws. And according to quantum mechanics, there's a probability density rho, which is expressed in terms of the wave function psi over there, and a current, sorry, that's 2n, which if you then use the Schrödinger equation, indeed you can show that these currents, probability density currents, and the probability density rho, that they satisfy this continuity equation. So again, we have an equation that the divergence of J plus the time derivative of t must be equal to 0. Is there a question? In fact, to show indeed that this equation over here is satisfied by these quantities, you have to use the fact that indeed the function psi satisfies the Schrödinger equation, but even it's more easy to write down the Schrödinger equation in a slightly different form. In here I wrote the Schrödinger equation with the linear derivative with respect to the time. But actually you can take sort of the square of this expression by taking twice the time derivative here and then squaring the Hamiltonian on the right-hand side. So I'll take actually the square of this operator acting on psi is also the square of the operator on the right-hand side, because what I gain from that is that I eliminate the square root in this expression. So the wave function which I have over here also satisfies what's called the Klein-Gordon equation. So this expression satisfies the Klein-Gordon equation. Which is written as dt squared minus lambda squared plus m squared acting on psi of x and t equals 0. Well, to be honest, this is not the most general solution of this Klein-Gordon equation. It's namely a solution which has omega k equal this solution, which is larger than 0. But this equation also allows plane wave solutions where omega k is replaced by minus omega k. So the most general solution of this equation has an additional contribution where omega k is replaced by minus omega k. And those solutions are not allowed because, well, this condition actually means that the energy of the particle is a positive energy, and so the solutions of this equation which have omega k smaller than 0 will be negative energy particles. And this fact that there can be negative energy particles also plays a role in the interpretation of this probability density, because this probability density must be positive, because we have always positive probabilities. Never we can encounter a negative probability, but this is a positive probability only when we allow positive solutions. Indeed, if I would plug in here the plane wave solution, which I wrote there on the blackboard, then you find that rho for plane wave solutions, we find that rho is omega divided by m, and J is K divided by M. So indeed, in order that this probability is positive, we must conclude that omega must be positive. So the negative frequency solutions of this equation will give also negative probabilities. Well, this is something that confused people a long time, and it was actually Dirac who was motivated by this problem of having negative probability densities to rewrite and look at different kind of wave equations which didn't allow any negative probabilities. And he identified the problem in with this equation in the fact that there's a second time derivative in this Klein-Gordon equation, because this will indeed give you in the probability density a single time derivative, and then allow for positive and negative frequencies, gives you positive and negative probabilities. So he wanted to write down a first order differential equation and then eliminate the probabilities and the possibility of negative probability densities. Well, what he discovered actually was the wave equation for spin half particles, and the way I can present it now is more like that, so that we do know now about the existence of spin 1/2 particles and something about the way that they're described in quantum mechanics. Well, actually, in non-relativistic quantum mechanics, we know how to describe spin 1/2 particles. They have two components, spin up and spin down. And so what I want to show now is how you can get from that description to the relativistic descriptions following a similar procedure that I did now here for the scalar, for the spinless field, which is so this actually what I described here is the wave function of a particle without spin. For a particle with spin, we have to do something else. So we're going to look at spin 1/2 particles. And write down the relativistic wave equation for a spin 1/2 particle. Just like, well, the wave functions in non-relativistic quantum mechanics for a spin 1/2 particle have two components, and they have one up component, which corresponds to spin up, and a down component. So we can write them down in terms of a two-component spinner, which has a function here and a function there, and that function can be written either in momentum or in coordinate space, and I'll actually write down here things in momentum space. So I'll have a function, wave function, a state of a non-relativistic spin 1/2 particle can be written down by a function chi of k, which has two components, chi up and chi down, which are both functions of k. Well, the spin is an operator which acts as 2x2 matrices. So the spin operator is h bar times a Pauli matrix, where the Pauli matrices for the x, y, and z components, or usually written as sigma 1, sigma 2, and sigma 3, are the usual expressions, and I'll just write them down here for completeness. Satisfying relations like that sigma I squared equals 1, and sigma 1, sigma 2 is minus sigma 2, sigma 1 is sigma 3, etc. There are many relations like that where you take the product of two of them, which are not equal, and then they give you the third one. And the square of each of those matrices is equal to 1. Well, in order to write down the relativistic wave equation, what Dirac did, he looked at this, what's called a spinner, which is a two-component object, and introduced the Dirac spinner, which is a four-component object. So he looked at a wave function psi, which is a vector written in terms of two spinners, which I'll call psi plus and psi minus. So each of those psi's is a two-component spinner of this sort. So this is actually four components together. So in particular, on these two components, you can act with the Pauli matrices, and we can now introduce 4x4 matrices, just like here we have 2x2 matrices acting on these two components. we have 4 by 4 matrices which we can allow to act on those 4 components. And the 4 matrices we first introduce are a matrix set of 3 matrices, alpha, which I denote with a vector, so it has 3 components, alpha 1, alpha 2, alpha 3, which are related to the Pauli matrices in this way. So you write down a 4 by 4 matrix in block form, where here I have a 2 by 2 matrix with 0 entries. Here I write down the 2 by 2 Pauli matrices, and here like that too. And so this is a 4 by 4 matrix, giving you 3 4 by 4 matrices, which together form a vector alpha. And then there's a matrix beta, which is almost like the identity matrix, except there's a -1. So these are identity matrices in 2 by 2 form. So this is a 2 by 2 identity matrix, and this is minus a 2 by 2 identity matrices. And here again there are 2 by 2 matrices with all 0 entries. So given these equations, then there's also a relativistic Dirac-Schrödinger equation, which instead of this Hamiltonian so this would be actually for a spin 0 particle, what it was described here. For the Dirac or spin 1/2 particle, this equation, so psi now is a 4-component object like this, and the equation which I have here takes the following form. The Hamiltonian on the right-hand side, H, is now an operator which involves these matrices alpha and beta. So the Hamiltonian is minus H alpha dot. So it's an operator which is a matrix valued operator because this matrices alpha and beta appear in the Hamiltonian. Let me write down now what, well, I can also write it down in more explicit form as one equation, which is the Dirac equation. Which is IH bar ddt psi equals this operator. Acting on psi. So that's the Dirac equation as Dirac wrote it down in first form. Well, what's you learn from this is that there now can be written down probability currents just like here. However, now we have probability currents which are much simpler for the Dirac particle. So these are the expressions for the Klein-Gordon particle satisfying the Klein-Gordon equation. For the Dirac spin 1/2 particles, there are also probability currents like this, but rho is now equal to psi dagger psi. So this is the inner product of this 4-component spinner with itself, but here you take the Hermitian conjugate, so it's complex conjugate, then taking the inner product. So it's a number which is a function of x and t, and describing the particle density, and the current density is an expression which is psi dagger alpha psi. And so what we gained now is that indeed there are no time derivatives or even spatial derivatives in these expressions, and this actually allowed Dirac to solve this problem also with probability of having negative probabilities. Well, we can write down the solution to the Dirac equation in a similar way as we did over there, and the solutions also look similar. As again, sorry, there should be a line like this, so this was divided here. So the solution to the Dirac equation is an expression like this. We have psi being equal to, again, an integral over k to omega k, where this is the same omega k, and again positive. And then there is a plane wave, just like over here. And then there's a spinner, which I call u of k. And u of k is a 4-component spinner which looks like this. It has a particular normalization. And then there's some function chi of k, or some, actually I should say it's a 2-component spinner chi of k, which is the same 2-component spinner which I introduced over there. And then the other 2 components are expressed in the same function chi of k, like this. It requires some algebra, but if you take this expression over here, where you take this u of k being the 4-component spinner you put here, then you can plug it into the Dirac equation and verify that the Dirac equation is satisfied. And again, these are the solutions which have positive energies omega. Actually, there's one thing you can notice, that if the particle is at rest, which means that the momentum factor k equals 0, so that's actually where you go to a non-relativistic regime, these 2 components indeed go to 0, and so you're left only with 2 components being non-zero of this Dirac spinner. So the Dirac spinner indeed describes particles with 2 polarizations, namely a spin up and spin down, as it should for a spin-a-half particle, because we have not changed the number of components really of the physical particle. A particle has 2 polarization states, an electron has 2 polarization states, and so we only should allow 2 independent functions in our solution. However, it turns out that eventually you can also include in the same formalism the positron particle, which is another particle, the antiparticle of the electron, and for that to be included, indeed you need all of the 4 components. So the fact that the Dirac field has 4 components tells you something about the fact that indeed we have electrons and also positrons. So I've written down these Hamiltonians and relativistic Schrödinger equations in explicit form, where the time and the place are written down separately. Actually, for relativistic theories, it's much more convenient to introduce a relativistic notation. And this is also how eventually we'll write down the Lagrangian say for the standard model and for quantum electrodynamics and so on. So let me introduce this relativistic notation and describe the basic equations here in that context. So in relativistic notation, so where we introduce x mu being x and t, and d mu being the derivative with respect to place and time, and I'll have a metric eta mu, which is used to raise and lower indices, which has, in my conventions, a signature -1, -1, 1. So mu actually here goes from 1 to 3 for the spatial coordinates and then 0 for time. And so I'll put time here with the +1, and for space I'll put -1. Now using these conventions, you can write down the Klein-Gordon equation as d mu plus m squared acting on the wave function, which I'll in this case write as phi of x equals 0. I changed actually the wave function from psi to phi for the scalar particle actually for a reason, namely that to distinguish it also now from the Dirac equation, because in the Dirac equation we'll have a spinner which has 4 components. Here this is just a scalar function without any vector structure, so it's really just a function, while the Dirac equation, to write down the Dirac equation, we have to introduce also matrices which are called the gamma matrices, which are related to the matrices alpha and beta, which I had over here and which I erased actually. So it's the alpha and beta matrices which I wrote down before, can be replaced by gamma matrices, and the Dirac gamma matrices which I'll call gamma mu, so which has the spatial, 3 spatial matrices, gamma I from 1 to 3, and then a gamma 0, and gamma is equal to beta times the alpha matrix, and gamma 0 is beta. So using this new notation, we can write down the Dirac equation in a very simple form: E gamma mu of I gamma mu d mu minus m acting on psi of x is equal to 0. So this equation, that's the Dirac equation, the same Dirac equation as I wrote here. What I basically did is multiply this equation with beta. If you multiply the left and the right hand side with beta, and beta is a matrix, remember, which looked like that. So it squares to 1, and multiplying this equation with beta, you'll find that indeed this equation is exactly the same equation as I wrote it down here. Also, the probability current densities can now be written down relativistically. You get the current J mu, which combines J and rho. And in here you see that J mu is equal to I over 2m phi star, well, okay. Replacing where I've written down here psi with phi, just because to relate it to the same phi which I have over here, you'll get the current density for the scalar particle, which is phi star d mu phi minus phi d mu phi star. And indeed, using the Klein-Gordon equation, you can verify that this current satisfies the conservation law, which in relativistic notation is just d mu j mu equals to 0. And similarly here, you'll find that the current j mu has a simple form as psi bar gamma mu psi, where I'll denote psi bar as being psi dagger times gamma 0. So for Dirac spinners, there's a bar notation which is not just complex conjugation or Hermitian conjugation. We also introduce a multiplication with gamma 0. And so then in this notation we can write down the currents as J mu is psi bar gamma mu psi. Well, what I described today in this first lecture actually is just the way that we describe relativistic particles, single particles without any interactions. But this will be important for now going to field theory and to describe eventually the rules for computing Feynman diagrams and for computing amplitudes, because precisely these normalizations and the way that these wave functions are written will enter in the Feynman rules, because the particles before they interact, of course, they are free particles, and so we should know what their wave functions look like. And then the next thing is to do is what describes how they interact, and then eventually you should translate it into particles that come out again, and again are non-interacting. So the way that we think about well, the collisions or even just all the interactions in field theory is that we have a quantum Hilbert space, or indeed the quantum wave functions of all the particles together, which when they are far apart are really just free particles. So they should just obey all the usual rules of quantum mechanics and of relativity, and this is how you describe those free particles. The way that we include now the interactions, that's where quantum field theory comes in. I haven't written down any fields yet. I've just written down wave functions. The quantum fields will come in later. Are there any questions so far? No questions? So the next thing to do is now indeed to go to a Hilbert space, not of single particles, because what I described now are just the wave functions of one single particle. But in real experiments, or just in the whole world, we have many particles, and so we need wave functions of many particles. Well, naively, what you can do is write down a big wave function, which is a wave function, say, if we have n particles, that it should describe the positions of all of those particles. Say we have particles at position x1, x2 up to xn, and this wave function should depend on a time t. And now for particles, well, you can think about, well, the particles when they're far apart, each of those particles will have independent wave functions. So to provide a basis of these, you can think about this wave function as being roughly the product, say, of the single particle wave functions x1 of t for, say, the first particle up to the last particle. Actually, these wave functions need not be the same wave function, so there might be, say, psi1 function for the first particle up to psi n for the final particle. And these wave functions you can think of as being, say, the plane wave functions, which I wrote down before, or something more complicated of this sort. So this might be a wave function of each of those particles, where each of the particle has a certain psi of k associated with it. Well, we also learn in quantum mechanics that we can have identical particles, and then it means that these wave functions have to be symmetrized. Well, the way that it will appear in quantum field theory is slightly different. We will actually take not just the wave functions of, say, n particles and go to a Hilbert space of n particles. We want to have a Hilbert space that can contain any number of particles. And the reason for that is that indeed in experiments the number of particles may change. The number of particles that we have at a certain moment may not be the same number of particles that we have at a later moment. Because of interactions, particles can be created. So we're going to build a Hilbert space with arbitrary number of particles, and this is called a Fock space. For that Hilbert space, we also have to describe, of course, a Hamiltonian. Well, first to tell you why it's wrong to take just this expression and say, so for the n particle Hilbert space, and do naively what we would do in non-relativistic quantum mechanics. In non-relativistic quantum mechanics, we would take this expression and write down a Hamiltonian, say, as just the sum of Hamiltonians of each of those particles. And indeed, when we have free particles, this is the right way to do it. But interactions will be the crucial thing here. the free Hamiltonian is simply the sum of the Hamiltonians of each of those particles. So it's something like sum over n, then the square root of nabla I squared plus m squared, of mi squared. If there are particles with different mass even, then you can write down a Hamiltonian like this, and where I ignored now the fact that they can have spin or so. So these are just simple scalar particles without spin. Well, naively you might think you can write down some potential, say, which describes interactions, just like in non-relativistic field theory of quantum mechanics, but this is not allowed. And the reason is that here you write down a term which involves points at different points in space, and relativistically it would mean that particles interact which are not at the same point in space and time. And then this is not allowed because of causality, in the sense that you cannot emit something which goes faster than the speed of light. So this is not the right way to describe interactions in quantum field theory. The way to do it is actually to allow particles to interact at the same point in space and time. And so interactions between different particles always involve interactions which are local in space. So I'll end with just telling you a bit about what's the Hilbert space of many particles. Then I'll go to quantum field theory tomorrow. So we're going to, for simplicity, look at the Hilbert space of one kind of particle, and we're going to allow the Hilbert space to contain Hilbert states of arbitrary number of particles, and the particles are identical. So we allow only allow symmetric Hilbert states. Well, the Hilbert space, which I'm going to describe, is called the Fock space. And it contains many states, but there's one unique state in a Fock space, which is the vacuum state, which is a state without any particles. So if I'm allowed to have any number of particles, I'm also allowed to have no particles. So there's one state, which is called the vacuum, which has no particles in it. Then the next level, we have one particle states, and I'll denote them by k if there's one particle with momentum k. So this is described by a wave function, which is simply the plane wave function, which I wrote down at the beginning. So the particle which I have here has momentum k and energy omega k. So it's a one particle state. This was the vacuum, no particles, and this is a one particle state. And it's normalized in such a way that if I take the inner product of two of those, then we have something which is diagonal, in the sense that there's a delta function in k space, so the k and k bar must be equal, and there's some normalization which involves the same omega k function. Again, omega k is the square root of k squared plus m squared. Now, if we have one particle states, we also have two particle states. And n particle states. And just without any interactions, all of those states are orthogonal, in the sense that if I take the inner product of this state with the vacuum, I'll get 0. If I'll take the inner product of each of those states with each other with different particle numbers, I'll get 0, unless there's something happening that allows interactions. So the Hilbert space so far, as I described it here, is just a free Fock space of particles where I have states with a number of particles which is a fixed number and can be n, any number n. I think I'm right at time now, and so what I'll continue now tomorrow is how from this description of the Fock space you'll go now to quantum fields and etc. So if there are questions, no questions. All right. Oh yes, by the way, tomorrow it's again at 11, so don't be here at 10.